Hello, y'all. Welcome to lesson 69 of reactivity 1.2.2 of my DP chemistry curriculum. Today we're going over Hess's law, which states that the enthalpy change for a reaction is independent of the pathway between initial and final states, and we'll be able to apply Hess's law to calculate enthalpy changes in multi-step reactions. So let's reiterate that. Hess's law says that the enthalpy change, delta H, of a reaction, I'll do a little R, is independent of the pathway of reaction. Basically, the idea is if you start on the X and you take a path and you're doing a winding path for the lost buried treasure and you end on the second X, well, this distance right here remains unchanged. Now, if a smarter pirate took this alternate path, it doesn't matter. Overall, the distance between the two pathways is still the same, and this is how it works for enthalpy. So if we have a reaction such as reactant goes to product, and this has some delta H, but maybe you can't do this reaction in your lab or it's just incredibly difficult. But what you can do is reactant to intermediate, an intermediate to product, and this is delta H2 and delta H3, the overall enthalpy change, regardless of if you take route 1 versus route 2, is the same, meaning that delta H1 is equal to the exact same as the sum of delta H2 plus delta H3. So this is Hess's law in a nutshell. What is so important about this also pretty much it allows us to allows to find any delta H 1, 2, or 3 provided the other two enthalpies. This is a really powerful law and powerful tool that we have in chemistry. And so one of the most common things you'll actually be asked to do with it during your DP exam is to solve equations. Usually they are in the multiple choice questions, and it'll be a quick solve, and that'll be about it. You may sometimes see it in a paper 2 or 3, or sorry, paper 1B or paper 2, but for most part, we're just going to be solving equations. So let's learn how to solve equations. Solving equations with Hess's law. All right, so sometimes we have some equation such as C5H12 pentane, and we're reacting it with oxygen. I'll add some states. Now this is called a combustion reaction because we have a hydrocarbon, and we're going to produce 6H2O, maybe in the liquid state, plus 5CO2, definitely in the gaseous state. And we're trying to find the delta H for this. And we have no idea what it is. Well, turns out we can usually find the delta H for the individual components of this. So we have a couple individual components. Number one, 5 carbon plus 6 hydrogen reacts to form C5H12. And we know that the delta H for this reaction is something like negative 173 kilojoules. For reaction 2, we can still do 5 carbon, but this time plus 5 oxygen, combusting it, and we get 5 CO2, and this delta H is going to be negative 1,970 kilojoules. Lastly, we have equation 3. That's going to be 6 hydrogen plus 3 oxygen, and that reacts to form 6H2O. and that delta H will be equal to negative 1,716 kilojoules. So this becomes a puzzle. We can say we can have each equation can reverse, so go the opposite way. However, delta H sign changes. So positive to negative or vice versa. So if we reverse the equation, like for example, we just fully swap this one, we bring our reactants here, products here, this would become a positive value, as the reverse is the opposite enthalpy of the forward reaction. We kind of learned this in our previous unit as we did bond enthalpy. So if you reverse it, you just expect the opposite delta H as the equation flips. Furthermore, each equation can be multiplied by a coefficient, but delta H is also multiplied, which also makes sense. If we were to, for example, double the amount of pentane we make, that would cost double the energy or release double the energy. So these two ideas kind of make sense with it. So now the thing is we have to just solve the puzzle of how to make our equation. So this equation at the top, how do we make this equation? Well, I like to look at the big molecules first. So we have pentane on the reactant side, and the only place pentane shows up is the product side. So what we're going to do is we're going to reverse number one. So we'll start with reverse equation one. So that's going to create new one. One now reads C5H12 reacts to produce 6H2 plus 5C, and the delta H of it is now negative 170 or positive 173 kilojoules. Equation 2 and equation 3 actually kind of work out. We want 5CO2 on our products, and we want 6H2O on our products. And these reactants, 5O2 and 3O2, together make our 8O2. And this 5 carbon will cancel with this 5 carbon after it's reversed. And this 6 hydrogen will cancel this 6 hydrogen after it's reversed. So what I'm going to do is recopy these two equations down to the bottom. And we can see with our new one, we'll say our equation -1. 6 hydrogens cancel with 6 hydrogens. 5 carbons cancel with 5 carbons. And if we add these equations up, we just sum them all, we get as follows. Pentane plus 8 oxygen, so C5H12 plus 8O2 reacts to form our 5CO2 and 6H2O. I think I wrote 6H2O first, plus 5CO2. And our delta H's also sum. So it's 173, negative 1,970, and negative 1,716. So we can add those up too, and we get our delta H of reaction is equal to negative 3,513 kilojoules. So this is how we use Hess's law. We just take the constituent reactions that make up the equation, mess them around, like flip them or multiply coefficients, and we get our final reaction. There's one other way to use Hess's law. So Hess's law with energy cycles. Oops. Energy cycle. diagrams. So an energy cycle diagram is kind of the diagram we drew up here, but this time we are going to choose our own intermediate looking at the reaction. So if we have carbon in the form of graphite plus 2 hydrogen as a gas, H2, we can react that to form methane, CH4, also as a gas. And we do not know what this delta H of reaction is. However, we can use our data booklet and possibly find that the combustion of graphite forms CO2 plus H2O. So this combustion, delta H1, is going to be equal to negative 394 kilojoules mole inverse. So kilojoules per mole. Hydrogen also will combust with oxygen to form CO2 and H2O. Well, it'll combust to form H2O. And this combustion, just like carbon will combust to form CO, not H2O. Let me actually make these arrows a little clearer. Give me just a moment here. So the carbon will form the CO2 intermediate. The hydrogen will form the H2O intermediate. Sorry. And I'll add some state symbols there. So this is negative 286 kilojoules mole inverse. And lastly, methane will combust to form both of these products. So we have our little intermediate here, and this combustion, delta H3, is negative 891 kilojoules mole inverse. So looking at our energy cycle all the way back at the top, we know that the energy required to make our intermediate plus the energy to go from our intermediate to our product is the total energy. So we can apply this logic. Delta H1 plus delta H2 should be equal to, now we need the inverse of this, negative delta H3. However, this, oh, sorry, whoops. Made a mistake. Plus the inverse of delta H3 should be equal to the delta H of the reaction, as that is our overarching goal here. The one issue we have that we have to make clear right away is I see this little value say kilojoules per mole. But I'm using 2 moles of hydrogen, not 1 mole. So I'm going to have to multiply my H2 by 2 just to rectify the fact that we have 2 moles here. So we need to make sure we have 2 moles, as this is a per mole value. All right. So there we have it. Our delta H of reaction is this, so I'm going to just rewrite it where this is on the side. Delta H1 is minus 394. Then we're going to take delta H2 plus a negative 286 times 2. And we're going to subtract a negative 891. And we get a sum for our delta H of reaction as negative 75 kilojoules per mole. And there you have it. That's also how we use Hess's law, by using these energy cycle diagrams. Anyways, I hope this helps, and have a great day.